So let's get started. We discussed in the previous lecture, we discussed how to determine the moment of inertia for common engineering shapes. We solve a problem for rectangle and also for triangle. We learned how to determine the moment of inertia for rectangle and for triangle. Now we are going to use the moment of inertia for the most common engineering shape in order to determine the moment of inertia for composite area. So here is the moment of inertia for rectangle, and here for triangle, and here for circle, and here for semicircle. Now we need to know how to determine the moments of inertia for composite area. Composite area, it means that it consists of simpler parts. You can divide it into triangles and circles and rectangles. And the good thing about that, if I know the moment of inertia for the simpler parts, I'll be able to determine the moment of inertia for the composite part. So the beauty about the composite sections or composite area, if I'm going to know, or if I do know the moment of inertia for each part, then I'll be able to know the moment of inertia for the composite part. Okay, so let's see how we are going to do that. We have certain steps need to be done in order to determine the moment of inertia for the composite section. First, we need to divide the composite section into simpler parts, into triangles, rectangles, circles, and so on. The first step need to be done. Then we need to know the perpendicular distance from the centroid of each part to the reference axis. Of course, you need to determine the moment of inertia about a certain axis. So we need to know the perpendicular distance between the centroid of that part and the reference axis. Also, we need to find the moment of inertia of each part about its centroidal axis. We are going to use the formulas that we discussed in order to determine the moment of inertia about the centroidal axis. So each part, I need to determine the moment of inertia for each part about their centroidal axis. Then we are going to use the parallel axis theorem to find the moment of inertia about the reference axis. In order to know the moment of inertia about a reference axis, I'm going to use the parallel axis theorem. Then I'm going to find the moment of inertia of the entire area by summing the moments of inertia of all parts algebraically. Algebraically means that the positive is going to be positive and the negative is going to be negative. Then, if the composite body has a hole, if you have a hole inside your composite body, then the moment of inertia is going to be found by subtracting the moment of inertia for the hole from the moment of inertia of the entire part, including the hole. So if I'm going to have a hole, the moment of inertia, when it's come to summation, is going to be negative. So let's see example where we can apply those steps. So here we have example 3. We need to determine the moment of inertia for that area shown here. So we have an area. It consists of a rectangle, and here we have a hole. This one here is a hole, is a circular hole. And we need to determine the moment of inertia about that reference axis. So we have composite area. Since it consists of simpler parts, we have rectangle and we have circle. And we need to determine the moment of inertia about that reference axis here. All the dimensions are shown here. So let's see how we are going to solve that problem. The first step needs to be done. We need to divide the area into simpler parts. So I'm going to say that I'm going to have rectangle and I'm going to have circle. Then I'm going to subtract the moment of inertia for that circle from the whole part to get this one here. So in the first part, I divided the composite body into two parts, rectangle and circle. Then I need to know the perpendicular distance from the centroid of each part to the reference axis. So here is the rectangle. The centroid is here. I need to know the perpendicular distance between the centroid and the axis X. So here is the perpendicular distance for the rectangle and for the circle. And they are the same for this case, special case, which is 75 millimeter. So it's very important to determine the distance between the centroidal axis and the reference axis. Then we are going to find the moment of inertia for each part about their centroidal axis. So I'm going to get the moment about this axis for the rectangle and about that axis for the circle. I know that from the previous lecture, I know that the moment of inertia for rectangle is going to be 1/12 bh cubed. B is here and h is there. Always h is going to be perpendicular to the axis of interest. So my axis is here. I'm going to take the moment. The centroidal axis is like that. The cube dimension is the dimension that perpendicular to the axis in question. Okay, so since the question about the x-axis, and that dimension is going to be perpendicular to the axis of interest, it means that the cube part is going to be this dimension, the h, which is 150 millimeters. Okay, this is a very important point. And also from the tables, we know that the moment of inertia about the axis passed through the centroid is going to be 1/4 pi r to power 4, the radius. Of course, in this case, whether it's x or y, it doesn't really matter because r is the radius. So now I'm going to determine the moment of inertia for this part and for that part. B here is going to be 100, h is going to be 150, and here the r is going to be at 25 millimeters. Then I need to use the parallel axis theorem to find the moment of inertia about the reference axis. Now I get the moment of inertia for the rectangle and for the circle. Now I need to determine the moment of inertia about that axis. I'm going to take advantage of the moment of inertia about the centroidal axis for the rectangle or for the circle. The moment of inertia for that axis is going to be the moment of inertia for the centroidal axis plus AD squared. D here is the difference, perpendicular distance difference between the two axes. I'm going to do this twice. First for the rectangle and second for the circle. Then I'm going to get the summation. So for the rectangle, AX, the moment of inertia about X, is going to be the moment of inertia about the centroidal axis here, which is this value here, 1/12 BH to power 3. We say that B is going to be 100 and the H is going to be 150. Then the area is 100 times 150. And dy is the difference here between this axis and that axis, which is 75 millimeters. Now I can determine the value of AX. Also, I need to do this for the circle. I'm going to use the same formula for the circle. AX, the moment of inertia about this axis, because of the circle here, is going to be the moment of inertia about the centroidal axis for the circle, which is 1/4 pi r square. We say that r is 25. The area is pi r square, and the difference between this axis and that axis is 75. So now I know the moment of inertia about X because of the rectangle and because of the circle. Then I need to determine the summation. So find the moment of inertia of the entire area. Now for the entire area by summing the moment of inertia of all parts. So I have rectangle and circle. I'm going to sum them together. But I need to take care here. The circle here is a hole, which means that the moment of inertia for this one is going to be negative. So the moment of inertia for this one, I need to put it negative because I have a hole, and this one is going to be positive. So if a composite body has a hole, then its moment of inertia is found by subtracting the moment of inertia for the hole, this one here, from the moment of inertia for the entire shape. Okay, so in this point, do you have any questions about this example here? Example 4. In example 4, we need to determine the moment of inertia for this composite area. You can see this composite area, and we need to determine the moment of inertia about that axis here, x. Also, you could determine the moment of inertia about that axis y. But here in this question, we need to determine the moment of inertia only about x-axis here. So the first step need to be done. We need to divide the area into simpler parts. How many parts do we have here? We have 3 parts. We have triangle, we have rectangle, and we have circle. And we need to take care of the circle because here we have a hole. When I'm going to sum all the moment of inertia, this one should be minus. Then we need to indicate the perpendicular distance from the centroid of each part to the reference axis. So this represents dy in the equations. So here is the reference x. For the triangle, I need to know the difference between the x for that triangle, x bar, and that x. Also for the rectangle, between the x bar and x, and also for the circle. For the rectangle or the circle, dy is the same. But here for the triangle, is going to be 1/3 from the 200. So it's going to be 200 millimeter over 3. So this one here is the dy for the triangle, and this one here is the dy for the rectangle and the circle. For the rectangle and the circle, the answer is going to be 100 millimeters. For the triangle, is going to be 200 over 3, because it's the center of gravity, or the centroid for the triangle, is going to be 1/3 from the base, in this direction or that direction. Now we need to find the moment of inertia for each part separately about their centroidal axis. We need to take the formulas from the tables. This formula here for triangle, and this one for the circle, and this one is for rectangle, and this one for the triangle, and this one for the circle. I need to determine, I'm going to use this one for rectangle, I'm going to use this one for the triangle, and this one here for the circle. The value of B for triangle is going to be 300 millimeter. The H is going to be perpendicular to that axis, which is 200. For the circle, the R is here 55 millimeters. And for the triangle here, the value of B is going to be 300 millimeter, and the value of H is going to be perpendicular to this axis, which is 200 millimeter. So now I need to recall the equation from the tables. I needed to put it like that so that I can determine the moment of inertia about the centroidal. I'm going to put par for this one and this one and that one to indicate that the moment of inertia is about the centroidal axis. So now I'm going to use the parallel axiom theorem to find the moment of inertia about the reference axis. So the reference axis is here. I'm going to use the parallel axis theorem in order to find the moment of inertia. So here I have the triangle, and here is the dy for the triangle. Like I said, it's 200/3, and for the rectangle, it's going to be 100, and for the circle, it's going to be 100. Now, in this problem, I'm going to do it as one step. I'm going to put them together as a summation. So I'm going to use this formula for the 3 parts. For the first part, I'm gonna assume the triangle is the first part here. Is gonna be ax dash. Ax dash for triangle is this formula. The value of B is going to be 300 millimeters, and the value of H is going to be 200 millimeters cubed. Then the area is going to be 1/2 times 300 times 200 for triangle. And I need to know the value of dy, the difference between the centroidal axis and the reference axis. Here is 200/3, and it's going to be to the power 2. Then I need to add the moment of inertia because of this rectangle here. So I'm going to apply that equation again for this rectangle. For ax bar, I'm going to use that formula here, 1/12 bh to power 3. So 1/12, the value of b is here, the value of h is there. This dimension is perpendicular to the axis. Then we are going to put it to power 3. Then the area is this one times that one, and the difference, like we mentioned, is 100. Then I'm going to add the moment of inertia because of the circle. And remember, this one should be minus because the circle here is a hole. So for ax dash, I'm going to use this one here. And this one depends only on r, and r is 75 millimeters. And the area is pi r squared. Also, I know r, and the difference here, the value of dy is 100 millimeters. So I'm going to sum all the components in order to find the moment of inertia for that composite body about x. And here is the answer. Okay, do you have any questions about this here? 5. So in this example, we need to determine the moment of inertia for the cross-sectional area for a member shown here. This time we need to know the moment of inertia about the centroidal axis, about this one and that one, about x and about y. We need the both of them. Like you know, the first step need to be done. We need to divide the area into simpler parts. We are going to have divided like A, B, C. Rectangle A, rectangle B, and rectangle D. Also, you could make this one like that. It depends on you. But in the solution here, we are going to consider the rectangle A. It has a height 300 millimeter, and the width is 100 millimeter. We have rectangle A, rectangle B, and rectangle C. Then we need to indicate the perpendicular distance from the centroid of each part to the reference axis. So the reference axis this time is here. Okay, and for x, and for the y is there. So if it's come to x, regarding the rectangle B, the distance is going to be 0, because the centroidal of the part B is the same as the centroidal for the composite part. Regarding A, is going to be like 200 millimeter. Regarding D, is going to be also 200 millimeter from here and from there. Then we need to find the moment of inertia of each part. Since we have rectangles already, then we are going to use only this formula here. Ix is going to be 1/12 bh to power 3. So remember that Ax, we have a little difference between Ax and Ay. If it's Ax, then the perpendicular distance is h, and h is going to be cubed. If it's about y, this time the perpendicular dimension is going to be b, and this time b is going to be cubed. So we need to take care of that point here. So first we need to determine the moment of inertia for the part A and D. Like you can see here, the part A is similar to part D. What we will do for part A is going to be done for the part D. So first we need to take the moment of inertia about x for the part A. First is going to be the moment of inertia for the centroidal for the part A, which is 1 over 12. The B is going to be 100, and the H is going to be 300 here. And the area is 100 times 300. And the perpendicular distance, the difference between the z-axis and z-axis is going to be 200, and it's going to be squared. For the D is going to be the same thing, the same process for D, because here the difference also between the centroidal X for D is the same as this difference between rectangle A and that axis, the reference axis here. So that is why we say that rectangles A and D, in the terms of calculation, A and D, they are going to be the same. Also, if you wanna determine the moment of inertia about the Y, here, the difference is going to be 250 millimeter. Also, the difference is going to be the same for rectangle D. So both of them, they are going to have 250. So this one here is dy, and this one here is dx. Also, here the h was 300. When it's come to y, the h is going to be 100. So we are going to cube 100. So now we determine the moment of inertia about x and about y for A and for D. Now what about B? For B, since the centroidal axis is the same as that axis here, it means that this part is going to be 0. No difference in x and no difference in y. For the rectangular B here, like you can see here, this part is going to be cancelled. So I'm going only to have 1 over 12 bh cube and 1 over 12 bh hb cube for x and for y. Now I'm going to make the summation in x-axis and for the y-axis. For x-axis, I'm going to multiply by 2 here because I have A and I have B. Okay. For that part, for B here, is going to be put as only 1. Similarly, about y, I'm going to multiply by 2, and this one is going to be as it is. Okay. Please try to make practice, solve problem as much as you can. You can try this here. Try to solve this problem. Okay, I'm going to stop here. So if you are going to have any question, please